All right, well, good morning. Welcome to another fun-filled day of calculus. The plan today is to start looking at different ways or different techniques of integration, because there's still all kinds of functions out there that we can't integrate because we don't have the tools yet. And that's what we're going to develop for the next couple of weeks here in chapter 3 is all about learning more techniques. And so that's what we're going to do today. We're going to start with integration by parts, and I'm going to guess we'll get into some trig integrals as well, and yeah, kind of go from there. But before I take over, I want to open it up to you guys. Any questions about the homework? Anything you'd like to talk about? Are we all completely head spun with these hyperbolic trig functions? All right, Chase, I need a section number, not just the problem numbers, please. And then Alexi, when you say, can I help with the end of 3.2? Can I get a little more direction from you? Arc length. Okay. So let's see here. So 2.9, 13 through 15, and then arc length from the end of 3.2. All right, well, let me switch over here. All right, so let's start with 2.9. Through 15. Okay, I don't know if we're going to do them all, but we'll at least talk about them there. Okay, so this one, we've got f is equal to x times cosh inverse of x over 4 minus the square root of x squared minus 16. And then they're asking us to evaluate this thing at its derivative at 9. Okay, so basically this is a differentiate the problem, right? Let's differentiate this thing and see what we get. Okay. Oh, okay, thanks, Alexi. Alexi just said to ignore her question, so done, ignored. All right, so if we're going to differentiate this thing, let's think about what we're going to have to do. Let me actually go to a whiteboard here. Get that there. Okay, so f of x is equal to x cosh inverse x over 4 minus the square root of x squared minus 16. All right, so differentiation. For the first piece, this is going to require product rule because we've got x times cosh inverse of x over 4. And then the other one's going to need chain rule because we've got something inside of the square root. So this is a bit of a blast from the past. Got to remember product rule and chain rule. So product rule, we start with the derivative of the first one times the second. So that's going to be 1 times cosh inverse of x over 4. And then we add to that the first one times the derivative of the second. Okay, so we need the derivative of inverse hyperbolic cosine. Cosh inverse. All right, so what's that one?
To be sine. Oh, like with an H, hyperbolic sine.
Okay, so sinh, yeah, okay. Not quite. If it was just regular cosh, then the derivative would be sinh. But this isn't regular cosh.
Is it the fraction of 1 over the square root of like x squared minus 1?
Okay, so it's something along those lines. Yep. Okay, so we got to go to the, excuse me, the inverse trig forms. And inverse cosh, where's my cursor? There it is. Let's come back over here. So when you just have y equals inverse cosh of, we'll call it u. Right? And so this one, as Susanna was saying, it's 1 over the square root of something. And what goes in that something?
Oh, I said it was x squared minus 1, but you can correct me if that's not right.
No, so just go back and you look at your notes, right? We're going to make it a u, though, right? So it was 1 over square root of u squared minus 1. Okay, so we're going to do that, except we have to put in x over 4 for u. So we're going to have 1 over the square root of x over 4 squared minus 1. But then we need one more piece here. What else do we still need for this derivative?
Multiplied by x over 4.
All right, close. Not x over 4, but real close. It's just going to be 1 over 4 from the chain rule.
All right. Derivative of that.
Yep, that's all good, though. You were definitely on the right track. Okay, so we still have the chain rule that we have to deal with, so that's going to get us a times 1/4. Okay, so that's that piece. I should have written that further over. And so now with the square root business, well, let's do a 1/2 power, so we get 1/2 x squared minus 16 to the minus 1/2. And again, we need the chain rule, and the derivative of what's inside there is 2x. All right, so there's the derivative. And now it's just a matter of plugging in whatever the number was. I think it was 9. All right, so we had to have product rule. Within that product rule was some chain rule. And the other one had some chain rule. Yes, there's lots of stuff we could simplify and reduce. But if all we're going to do is plug in a number, plug in a number. And probably the biggest issue is going to be this one, the cosh inverse. Because like when we plug in 9 there, I doubt most of you know what value gives you a hyperbolic cosine of 9/4. I certainly don't, but your technology does. All right, any scientific graphing calculator that's worth anything has inverse hyperbolic cosine. And I promise you that like Desmos and Symbolab and the various online things will have it as well. All right, so okay for this one. All right, so thank you. I think that helps enough to do 14 and 15. Okay, cool. Well then, works for me. All right, so then I think we're good in terms of that. And Lexi said to forget about hers, so I think we're good, right? Okie dokie. Well, then I'm going to go ahead and hop up to the whiteboard and we'll start talking about integration by parts. All right, so as promised, we're going to start looking at other techniques of integration, other things that we can do to try to integrate things that we don't know. All right. And the first one, I'm actually going to start with a real simple kind of function that we might want to integrate. Suppose I said, let's find the integral of x times the cosine of x. Ooh, not very exciting, right? But it's just x times cosine. Those kinds of forms show up not infrequently. So pretty simple question. But you think about the techniques that we know, right? Right now, well, there's is this a form of a derivative that we recognize? And the answer to that should probably be no, right? Because we don't have any nice functions whose derivative is x times cosine. So, all right, we're out there. And then really our only other technique is to use substitution. So think about doing a substitution, u equals x. Well, that's silly. It just turns this into u cosine u du, same form. So the other choice would be to let u equal cosine of x. But if you think about doing that substitution, its derivative is going to bring in a sine of x, which we don't have, and trying to substitute in for the sine of x is going to be difficult, and no, right? So unfortunately, substitution isn't going to help either. So we need something different. And what we'd really like is some sort of a product rule for integration. Well, maybe we don't like that, but that would be useful, right? If we had some sort of a rule for when you have two functions being multiplied, like it was great for derivatives, it'd be nice if we had something for integrals. And that's what integration by parts is. So let me remind you about the product rule real fast. I mean, we just used it in that homework question, but remember the product rule. It said if we have two things that are being multiplied and we differentiate them, then you get u prime times v plus v prime times v. Okay. So that was the product rule, which means, of course, if we were to integrate both sides, we'd get the same thing, right? So let's do that real quick. Let's look at taking an integral of both sides. That leaves over here u times v is the integral of the derivative. They undo each other. And that's going to equal the integral of u prime times v plus the integral of u times v prime. Let's just integrate them separately. And I'm just going to move things around just a little bit. And rewrite this. So we're going to get the integral of u dv is equal to uv minus the integral of v du. So in essence, all I did, I moved this piece over here. And then I wrote them as dv's instead of v prime. All right, well, that last line, this is the one you want to put a box around. And this is the formula for what we call integration by parts. It gets that name because what we're going to do is we're going to split the integral into two pieces, the two parts. One part we're going to call u, the other part we're going to call dv. And then we're going to use this formula to find the integral. All right, so the formula comes strictly from the product rule of derivatives, which should make sense, right? The product rule of integrals should be related to the product rule of derivatives, but notice that it's not the same. All right, it just is. Well, let me show you how that plays out with this example. So here's what we need. We need a u and a dv. We need to know what those two different pieces are. And so we're going to break this apart. So here are going to be my choices to start with. Let's let u equal x. And how about we let dv equal cosine x times dx. I literally split it into two pieces right here. This is not the only way to split it. We'll talk about how you pick, like what's going to be most likely to work. But you can break it however you want. Just like thinking about with the product rule of derivatives, right? You can swap things around and it doesn't really matter. So same kind of deal here. Like I just chose u to be the x and dv to be the cosine x dx. I could have let u equal cosine. Then dv would have been x dx, and it doesn't really. All right, now let's look at what we need to do our formula. We need to know both u and v. Well, I already have u, but I don't have v, I have dv. But I'd really like to be able to have a v equals. And then if we look at the other side, other piece here for the integral, we need a v and a du. Okay, well, I need to get the v. But I also need a du. I don't have du, but I do have u. So I still have these two pieces that I have to figure out. But this is easily enough done. To get my du, I just have to differentiate u. So in this case, du is going to equal dx. I mean, we do that all the time when we do a u substitution anyway, right? All right, so then what about the v? What am I going to do to get v? Anybody see what I need to do here?
Just integrate cosine x dx.
Yeah, I'm going to integrate my dv. Right? Because if I integrate dv, that gives me v. So I'll integrate my cosine of x. All right, well, the integral of cosine x dx is sine of x. And yes, technically I should have a plus c. We don't have to worry about the plus c. It'll all come out, I mean, it all gets played out along the way. All right, so if I were to break it this way, choose my u to be x, my dv to be cosine x dx, here are my du's and my v's. So let's put it into the formula, and let's see what this gives us. So we're going to get u times v. So that's x times sine of x. And then we're going to get minus the integral of v du. So v times du is sine x dx. All right, so notice a couple of things. First of all, we still have an integral. When you do integration by parts, you still get an integral. So we're not done. After this first step, we're not done. However, notice this. Notice that what's in this next integral is easier. In fact, it's doable, right? We all know the integral of sine. Well, we should all know. We should all know the integral of sine. but at this point we know the integral of sine. So when you do integration by parts, you're basically swapping integrals. You're taking a more difficult integral and turning it into an easier one. At least hopefully you're turning it into an easier one. But now we can do this. Let's go ahead and finish this off. So the x sine x, of course, that's still just x sine x. The integral of sine is a negative cosine. So when I subtract the negative cosine, I get plus cosine. And then it's at this point, I'm going to put in my plus c. So this integral, the integral of x cosine dx, is right there. It's x sine x plus cosine of x, and then plus c. All right, well, there you go. You just did integration by parts. You did a product rule of integrals. If you want to think about it, integration by parts is a product rule for integrals. All right. So that's the process. You're going to pick your u and your dv, then you differentiate u, you integrate dv, and then put everything into the formula. So it's very procedural, right? It's a cookie cutter recipe kind of thing, which we tend to like. The hard part is going to be deciding on the u, because sometimes that can actually backfire. All right, so before I move off of this guy, any questions on the steps in the process? All right, well, check this out.
Actually, Bruce, I was wondering.
Yeah, go ahead.
Sorry, can you kind of, I mean, it seems pretty simple enough, but that's what, like, how do we just break this into this parse and just say, like, this is now u and this is now dv? Like, is it just, that's what, like, I don't know, does that make sense or no?
No, I totally understand what you're saying. And my answer, the reason I started chuckling is when he's like, how do they do it? It's like, I don't know, I just chose it. Like, literally, I just went, I'll take the first part is u and the second part is dv.
But that's what I'm saying. Like, we're just able to just break all of a sudden. That's what I feel like the product rule, I don't know, I just felt like it would be so much more complicated than just like breaking it up into two pieces, then rearranging it like that. Like, I feel like there would be some kind of weird multiple that, I don't know. Yeah, I guess it's just that easy. I don't know. Okay, cool.
I mean, well, if you pick properly, because you can
Right.
pick your u in a bad way that makes it that it doesn't work. But yeah, sometimes that happens. But yeah, just split it apart however you want. It literally is just like just that. So there is no catch other than there are choices for your u and dv that are not going to work or are going to be more complicated. And I will show you. I'll show you how you can, like, there's a pretty good way of choosing your u when you have multiple choices like this. But yeah, no, I like hearing you say it seems like it should be harder, but it's not. Yeah, it's always refreshing when that happens in calculus, because it always seems like it goes the other direction, right? It usually seems like it should be something that's really easy and then it's crazy hard. No, this one, it's just a matter of following the formula. You just got to pick. But I'll get to that in a second about how we can ensure or more set ourselves up for more success by how we pick you. But what I was going to say, I love integration because I can always check myself. I can always check my answer and see if I did it right by differentiating, right? If I differentiate what I have at the end, I should get what I started with. So something that you will see me do a lot, and this is something that I highly recommend that you do, is check yourself. Let's differentiate x sine x plus cosine of x plus c. All right, so we got x sine x plus cosine of x plus c. So for the first part, we need product rule. So the derivative of x is 1. We got 1 times sine minus, or sorry, plus the derivative of x, or x times the derivative of sine, which is cosine. The derivative of cosine is a minus sine. And of course, the plus c goes away. We see that the sine and the cosine, or sorry, the sine and the minus sine cancel each other out. One thing cancel. Now we're left with x cosine of x, which is what we started with. And so boom, I know for sure this is the antiderivative and that I got it right. So I highly recommend doing this, especially if you get something that you feel like, oh my God, that doesn't seem right. Just do a real quick derivative and you can see if it matches. All right, so also with this one, before we run away, let's try it by picking a different u. And I want to show you what happens. So we already know we got the antiderivative. But let's say we had broken it down in a different order. We had chosen u to be, say, cosine of x and dv to be x dx. So here's another way of splitting it up. So now I'm calling the cosine u, and then the rest of it, x dx, is my dv. So let's try doing the same thing. We need a du and we need a v. Well, these are also easy enough to get. Du is going to be a minus sine of x dx. And then v, if I integrate this, is going to give me x squared over 2. So that's what it would look like if we chose u and v differently. All right, well then this integral is going to equal u times v. So x squared over 2 times cosine of x, and u times v, minus the integral of v du. Well, it's minus of minus, it's a plus. So now we're integrating x squared over 2 sine of x dx. So again, we're using the same form, uv minus the integral of v du. So again, we swapped the integral of x cosine of x for the integral of x squared over 2 sine of x. Now, I don't know about you, but I look at this one down in purple that we just got, and that looks a lot worse than what we started with. What makes it seem worse to me is the x squared. All right, so this would be an example of a bad choice for u. Letting u equal cosine of x in this case is actually making things worse. It's increasing the complexity of our integral. And that's never a good thing. All right, so how do we minimize this? How do we minimize the likelihood that we pick wrong for our u? Well, here's what I want you to think about. Think about what we're doing with the u and the dv's. The u we're differentiating. The dv we're integrating. So if we're going to be smart about this, we want to make that as easy as possible, which means really don't worry about the u, because differentiating at this point, it doesn't matter what I give you, you can differentiate. You know all the rules. However, integrating, we're really limited on, right? So integration is the thing that limits us. So what we want to think about when we decide what part is u and what part is dv, we want to think about what part is easiest to integrate. Gives us the nicest integral. So basically we want an easy thing for dv and we want the difficult thing for you in general. Now, I know looking at this, you see x and cosine of x, and they both seem pretty easy. But there are going to be other times when it's pretty clear. But I can do you one better. I can actually give you a little mnemonic device, those little memory devices, help you remember what order you should pick you. All right, so here it comes. When picking you, we're going to use what's Liate. So pretty much if you do this, if you pick you this way, you're going to be good to go. All right, so Liate, all of those letters stand for something. So put them here. All right, so the L stands for logarithms. If you see logs in your integral, pick them to be u. Because we can differentiate logs all day long. But integrating logs, does anybody even remember what the integral of log is? So when I say log, Adam, I mean natural log. In calculus, we can really just turn everything into natural logs. So yes, I'm specifically talking about ln. But also if you've got, other stuff. So the derivative of natural log is easy, 1 over x. The integral of natural log is x log x minus x. Yeah, obviously, right? Okay, I'll actually show you how we know that that's, or how we could use integration by parts to get that. But if you see logarithms, specifically natural log, put that in your u. Let the rest of it be u. Okay, so then the I, this stands for inverse trig. Because it's kind of the same deal. Like differentiating inverse tangent is easy. 1 over 1 plus x squared. Integrating inverse tangent, not so easy. Okay, so that's what the I stands for. The A stands for algebraic. All right, so what the hell is algebraic? So algebraic, this is polynomials, roots, etc. Okay, so these are things like x squared, square root of x, 1 over x, things like that. Because those start to be a little bit more complicated to integrate, and they're not as bad as logs and inverse trig and stuff, but they're kind of the next higher priority. Then the T stands for trig. And then the E is exponentials. So basically, if you are given an integral, look at the parts. Look at what the natural parts are to break it apart. And rank them on this list. And whichever one shows up higher on the list, pick that to be u. Okay, so it's a literally go down this order. So come back to the one that we just looked at. Right, the very first one we did here. We had the integral of x cosine of x. So our choices really are x or cosine of x. The cosine of x, of course, is trig. X is algebraic on algebraic function. So if we look at our list, the one that is ranked highest is our algebraic, the x. And so that's what we picked, and you saw that it worked out pretty well. So this isn't a 100% always will work, but it's a like 90% of the time it's going to work. When it fails, well, basically, if you ever run into a situation where your next integral is worse than what you started with, back up and switch something, try something different for you. All right, so be aware that that's going to happen to you. There are going to be times where you don't immediately pick the correct u. Be okay with that. Okay, be okay with that. It happens. It happens to me. Sometimes I pick the wrong u. All right, but you can see it. Follow the octet in general. It works pretty well. All right, so let's try some more. Let's play around with some other forms, some other things that are in here, and sort of see what happens. All right. So the other thing I'm going to do, I'm going to put up here in the corner of the board the integration by parts formula, just so that we got it. Integral of u dv is equal to u times v minus integral of v du. Okay, so I will try to remember not to erase that so I can reference it, but we'll see how things go. All right, so let's try this one. Let's say we've got the integral of x squared times the natural log of x. All right, so the two obvious choices would be x squared or natural log of x. If we go to our little mnemonic device of Liate, see the log highest on that list. So that's what I'm going to let u equal. So then dv is all of the remaining stuff. Okay, so we're going to see if this works. So we need the derivative of natural log, which is nice and easy, 1 over x dx. And then v is the integral of x squared, which is x cubed over 3. All right, so then my integral is going to be u times v, so x cubed over 3 times the natural log of x, minus the integral of v du. Well, v was x cubed over 3, du is 1 over x dx. Okay, so we got x cubed over 3 log x minus, let me just simplify this a little bit, it's 1/3 the integral of x squared. So I'm going to pause here for a second. Chance to catch up. And also, just to point out again, we traded out integrals, right? We had integral of x squared natural log, and now we have just integral of x squared. I'm happy because I went from a difficult integral to an easy integral. And in fact, I'm going to be able to bust this out right now. So this is going to end up equaling x cubed over 3 natural log of x minus 1/9 x cubed plus c. And there you go. There's the integral of x squared log x. So as promised, good choice for you. We now have the integral of that. All right, so to kind of go back to what Adam said when he was like, there's got to be a catch. Doesn't seem like there was a catch here. Let's just follow the form. I mean, we basically are undoing product rule. Okay, but me saying that there isn't a catch after just showing you 2 examples isn't really fair, because of course you know that there are going to be some kind of quirky things. So let me show you some of the quirky things that happen with integration by parts, some things to be aware of. All right. But before I go there, are we good with this? Thumbs up? Thank you, Stephanie. At least I got one thumbs up. All right, getting a few. Okay, so let me show you some quirks. So let's look at this guy. And it's probably not going to seem like it's much of a quirk, but let's try the integral of x squared e to the x. So nice and easy, x squared e to the x. All right, so according to Liate, what are we going to choose for our u? Which of these pieces?
The x squared.
That sounds good to me. X squared is algebraic. E to the x is exponential. Exponential is at the bottom of the list. So we'll let u equal x squared, dv equal e to the x dx. So we differentiate u. So du is 2x. And we integrate v to get v. Well, integral of e to the x is e to the x. That's why we love having e to the x in our dv, because this integral is really easy. All right, so we put this together, we're going to get u times v. So x squared e to the x minus the integral of v du. Right, so u times v right here minus the integral of v du. I just pulled the 2 out front. All right, so let's kind of take stock again. Where at this point we traded out an integral of x squared e to the x for an integral of x e to the x. Okay, cool. It's a less complicated integral. However, I don't know how to integrate x e to the x. I mean, I know how to. I don't know what the integral is, and I doubt you guys do either. So does anybody see what's going to have to happen here?
Repeat the process.
Yeah, we're just going to do it again. We're now going to do integration by parts on the x e to the x. All right, so this will happen. You will run into situations where you have to do integration by parts multiple times in a process. Okay, but the way you know you're on the right track is if the integral you get is easier. If your integral starts looking worse, you went the wrong way. All right, so let's do integration by parts again. All right, so for this one, the u I want is going to be x. And again, the dv is going to be e to the x dx. So I've got an algebraic part. So then the du is just going to be dx. The v is going to be e to the x. Right? I differentiate and I integrate. And then I put this all together. All right, so here's where we are. We had the x squared e to the x from the first piece. We have minus 2 times. Now let's put in the integration by parts here. I've got u times v, so x e to the x minus the integral of v du. So again, we traded out an integral of x e to the x for an integral of e to the x. It's better. I like that integral better. And in fact, I can do that one. So let's see what we get here. We have x squared e to the x minus 2x e to the x plus 2 times the integral of e to the x, which is e to the x. And I throw on my plus c, and there you go. There's the integral of x squared e to the x. That's the function whose derivative is x squared e to the x. And again, you can check it. It's going to work. It just required us to do integration by parts multiple times. All right, so that will happen to you. Sometimes we have to repeat the process, but as long as that integral is getting nicer, you're on the right track. All right, so that's the first kind of quirky thing that you need to see. All right, well, let me show you another one that's also pretty easy. At least it's easy looking. How about this guy? Let's look at the integral of e to the x cosine of x. All right, so what does Liate suggest as our choice for u?
Cosine x.
All right, cosine. Sounds good to me, right? T comes before e, so trig comes before exponential. So let's let u equal cosine of x. So dv is e to the x dx. All right, so du, the derivative of cosine is a minus sine. V, an integral of e to the x is e to the x. So by integration by parts, that gives us u times v. So e to the x cosine of x minus the integral of v du. So that's going to be a minus, right? So it'll be plus the integral of e to the x sine of x. All right, so by picking u and v this way, you get here. Okay, so started with this integral. We got this new integral. But if you were paying attention to the last example, you see this and you go, oh, that's not that big of a deal. We're just going to do it again.
This seems like it's just going to go around in circles.
Yeah, it is. If we do this, say, okay, well, let's let u equal sine of x and dv equaling e to the x dx. Then du is cosine and v is e to the x. All right, so let's put it in. And where are we? So we've got e to the x cosine of x, and then plus u times v. So cool. E to the x sine of x minus the integral of v du. So minus the integral of e to the x cosine of x dx. And at this point you go, all right, I've got another integral. So I'm going to do it again. But yeah, Rigny was exactly right on there. At least I think that's what I heard. Yeah, we're just going to go in circles. Because if I do e to the x cosine of x, that's the same integral that I just started with. Okay, so clearly we chose u poorly, right? This was a bad choice for you. Because it's just leading us to going around in circles. All right, so what are we going to do? What do you think we should do at this point?
maybe try again, but use the exception of putting an exponential first.
Yeah, I think that sounds right. Like when in doubt, if your choice for u doesn't seem to work, all right, pick the other thing. Because I told you Leonte doesn't always work, right? So instead of doing u equaling cosine, let's try u equaling e to the x. Okay, so we'll let u equal e to the x. So then the dv is going to be cosine of x dx. All right, well, those are both easy enough. Du, its derivative is e to the x dx. Integrating cosine is just sine. Okay, so we get u times v, e to the x sine of x, minus the integral of v du, minus the integral of e to the x sine of x dx. And if it's starting to feel like Groundhog Day, it should. Because if you look at what we just tried when we went with the u equaling cosine, as prescribed by Leonte, we ended up with another integral of e to the x sine x. And I bet it's not going to surprise you that if we do this again, same choice where we let u equal e to the x and dv equals sine of x dx. All right, so you follow that process, and then you use the integration by parts formula. We're going to get a u times v, so that's an e to the x times minus cosine of x being subtracted. E to the x cosine of x. And then the integral of the v du leaves us with an integral of e to the x cosine of x dx. All right. You can tell I've got a little shit-eating grin on, but this cracks me up. Where you go, it doesn't matter how you pick your u or you pick your v with this form. Yours is going to run into this. I just keep doing these integrals forever. Get into this horrible cycle. Okay. So it's at about this point you probably just go, yeah, fuck it, I'm done.
You tried the whole thing.
Say again. Oh, try the whole thing. Let u equal e to the x cosine of x.
I don't know if it would help. I think it would just make it even worse, but
it would make it
out
worse,
there.
But I like how you're thinking, Susanna, because that's the option as well. We could let the entire thing be u. And in fact, I'll show you where that comes in handy for other things. But yeah, so at this point you just go, all right, well, I guess I'm done. I'm not even. Well, I want you to just check something out. Forget about all this other nonsense. I just want you to look at what we started with and where we are. Right? This was the integral that we were trying to solve. The integral of e to the x cosine of x dx. Notice that that integral shows up over here as well. So it turns out we can now finish this if we use algebra. So check this out. I'm going to move this to the other side. I'm going to add an integral of e to the x cosine of x on the right. And I'm going to also add it here on the left. So that gives me two of these. Okay? Two integrals of e to the x cosine of x dx are equal to e to the x cosine plus e to the x sine. Plus c. Don't worry about that at the end. But now if I want this integral, I just have to divide by 2. All right, so check it out. We got it. We have the integral of e to the x cosine of dx. That's the function. I mean, don't believe me, differentiate it. And you'll see that what you end up with is e to the x cosine of x. All right, so this is how this one plays out.
if, as you're going, you run into the same integral that you started with, that's not a bad thing. That's actually a really good thing. Because then you can just do some algebra to get your answer. You can move that integral that you just got onto the other side and then work your way there. Okay, so I know it's bringing back our love-hate relationship with algebra, but algebra's got some nice little things to it, and this is one of them. It can definitely help us when we run into one of these cycles of integration by parts that just never seems to end. All right, so just watch out for that. That's going to happen occasionally. The reason it happened here is because cosine, its derivative is cyclical, right? And e to the x is always the same. So we end up with forms that are identical eventually. There aren't a lot of things that will do that. There are not a lot of functions that will do that. Right? So, but when they happen, you got to do. But again, it's just follow the rules, put in your pieces parts. All right, so we okay with that? All right, well, let me show you this guy. When I introduced integration by parts, I said it was a product rule, and that's primarily what we use it for. But it turns out you don't have to have multiplication to be able to use integration by parts. And to show you what I mean, I'm going to bring back our good friend, natural log of x. So all I want to do is get the integral of natural log. Now we already know what it is. Right? It's x log x minus x, because I just told it to you. Not just now, but when we were doing it, I just like, all right, here it is. I showed you that it worked by differentiating, but there never was a, how the hell did you get that? Right, never showed you. Well, here's how. So let's look at just plain old natural log of x dx. So looking at that, you may not think use integration by parts. However, we can definitely use integration by parts. If I pick my u, my choices are, well, I don't have choices. I've got natural log. I either put that natural log in my u or my dv. And obviously putting it as a dv is a bad idea, because then I'm just having to integrate the same thing to find my v. So watch what happens here. Du is 1 over x, and then v is equal to x. So if we use the integration by parts formula, we get u times v. So x natural log of x minus the integral of v du. All right, well, x times 1 over x is just 1. So this is x log x minus the integral of dx. And of course, the integral of dx is just x. And there you go. That's why, or that's how we could have found the integral of natural log of x. So that's where that formula actually comes from. So check this out. Integration by parts. You can actually use that to try to integrate things that you have no clue what their integrals are. Just go to splitting it into pieces and go. So I want to show you another one. Let's do this. Let's find the integral of inverse tangent. So that's another one that we know it's derivative, but we have zero idea what its integral is. And I'm actually quite certain that when we did inverse trig stuff, I didn't even tell you what their integrals were. I didn't even do you the favor like with natural log. Well, let's see if we can find it now. All right, so if this is going to work out, we got to let u be inverse tangent. And of course, dv is going to be dx. So du, hopefully you guys remember the derivative of inverse tangent is 1 over 1 plus x squared. And then the integral of dx again is just x. All right, so let's put it into the form. We're going to get u times v. So x times the inverse tangent of x minus the integral of v du. All right, so we now have to integrate x over 1 plus x squared. Can you do it? Actually, the question really should be, do you see how to do it? Because I know you can do it. We have a technique for this one. Anybody recognize it? Yeah, thanks, Adam. It's u sub. If you let u be the bottom, 1 plus x squared, its derivative is going to be a 2x dx. So this is going to be a log form, right? Or that's the other way to remember it. Logs, if the derivative of the bottom is on the top, it's a log. So this is going to give us x times the inverse tangent of x minus 1/2 natural log of 1 plus x squared. I just did the u sub fast in my head. You can go back and work on it if you need to see it. All right, well, there you go. There is our integral of the inverse tangent. It's certainly not pretty, but there's the antiderivative. All right, but there you go. There's integration by parts. It's really formulaic. Use this formula. Put the pieces in. You're going to end up with another integral to do, but hopefully that integral is easier. So you can think of it as a product rule for integration, but it doesn't have to actually be a product. It can be done. It can be used for standalone functions as well. Okay. So cool. Integration by parts is kind of useful.
I have a question.
Sure, Suzanne.
I've seen people do it where they make like 2 rows. Well, obviously, I think I've seen longer problems, but like they make a row of u and then the dx. I don't know if you know what I'm talking about. Like they make it vertically. That way they don't need to do like 2 steps separately. I mean, I think it's kind of more confusing, but it like saves space. Where they go down. It's like you have all the subs that you're going to do in that integral and then all the part, and it goes like down across. Or is that something else?
I have no idea what you're talking about. But
I might email you a picture if I can find an example problem.
And it could be, it's just a different way of organizing it. Because I don't think that there's a faster way. You know what I mean? Like, because it is what it is. It's you pick your U, you pick your DB, and you got to find the missing pieces. So I'm not entirely sure what you're talking about, if there's a different process or whatever, but it really is just find your pieces and put it into the formula. You don't have to organize it like I do. It's just, this works really well for me. Yeah, so maybe send me a picture so I know what you're talking about, because off the top of my head, I don't know what you mean by that.
I think I did find an example. I don't know if you could see it really well though.
Hold on a second. Switch up here. Do that for me.
Can you see that?
I do see that. Okay, so that's a trick for the repeated.
Yeah. Where it's just like you make 2 rows. So like, would that be easier or would this be easier? Or is it like dependent on case?
It's gonna probably depend on the case and depend on the person. So my advice is for you to practice it, or try it out both ways and see which you like. So that's what I suggest, and then you'll find which one works better for you.
Great, thank you.
That sounds more like a personal thing. Like anytime anybody asks me is this better, is this easier, that's a personal preference. So try it out, see what you think. But now I know what you mean. All right, so integration by parts is awesome, really, really useful. You run into it a lot, but it still doesn't take care of everything. So we need to talk about more forms. And what I want to start into with our remaining like 25 minutes here are some of the trig forms. And I apologize in advance for those of you whose trig is weak. If your identities are not very strong and you're not very comfortable with them, this is going to suck. I'm not going to mince words. All right. This is the point in calculus where you're going to really wish you had paid lots of attention in trig and gotten that stuff down. I will help you. I will definitely help you, but the stronger your trig is, the easier this is going to be. Okay. So we're just going to start with some trig forms, and the tricks we're going to pull for some of them. All right, so expect trig for the rest of today, all of Friday, possibly even some next Monday, right? Because there are a lot of things that are incorporated here in our trig form. Now, for the basic trig, it's easy, he says, right? Like integrating sine, integrating cosine, or integrating all of the things whose derivatives. So why are Adam and Alexi going to be fine? Are they super strong in their trig? Is that what you're saying there, Ragney?
I just noticed those guys are always like super on the ball with the trig, and
Right.
I am, on the other hand, not.
Well, let's see. Adam, were you in my trig class last year? I think you were.
Yeah, I was.
Yeah. Okay. So and then looking at this list, there are a couple of you. I know Jessica took trig with me. I think Tim did. I don't know. It's all a blur. But yeah, some of you have no excuses. The others, we can blame it on other teachers. But okay, so in terms of the identities, there are going to be just some key ones that we use a lot, depending upon what trig form we have. But the first one I want to show you is, what if you have a form that's sine of x to the power times cosine of x to a power. Okay, so I'm just putting these as letters K and M, so they can be whatever we want them to be. Okay, but these are going to be things like the integral of sine cubed cosine squared, right? So insert your favorite powers for sine and cosine. All right, so we're going to be looking at how do we integrate things of these different forms. All right, so it turns out that for these, they all come down to one of two identities. Okay, I guess there's a third. I think it was 2 sets, but here are the identities that you definitely need to know to help integrate things of this form. The first one is the granddaddy of them all. Good old sine squared plus cosine squared equals 1. I imagine most of you have that one down. That guy's big. All right, but then the other ones that we need, or are going to need for some of these, are the power reduction identities. And those are the ones that look like this. And honestly, I'm just running through my head real quick for which form is which. Okay, so this is the cosine of 2x plus 1. And, oh, I think I've got it backwards. Hold on a second. Don't write that down just yet. I gotta redrive them. Give me a second here. Nope, I got it right. Okay. This is the this is the proverbial man behind the curtain, right, from the Great Wizard of Oz. The power reduction identities come from these guys. Yeah, I know I'm good with my cosine. Now I'm starting to question my sine.
Bruce, I have it that isn't it? It's 1 minus cosine.
Dude, I'm one step ahead of you. Relax. Yeah.
Oh, I'm sorry. I think my internet's freezing. My bad. I think I just
you're all
lost you
good.
there.
I was making a joke. It's okay. I caught it at the same time. All right. So these are your power reduction identities. They're going to be useful, as you'll see in just a second. All right, so remember these. Now, I'm not saying necessarily that you have the power reduction memorized, like you just saw. I don't have them memorized. I can rebuild them if I need to. But you'll see why these are useful in just a second. All right, so in order to integrate these trig forms, what we really want to look at are the powers. And there are going to be 2 different cases depending upon what these powers happen to be. All right, so the first one is case number 1. K or M is odd. Okay. So we're going to look and see if one of those powers is odd. And then the second case is both are even. So this is going to be a pattern recognition kind of thing. You're going to look at the trig, what you're integrating, and you just have to figure out what's our pattern. It tells you which case to go with. Okay, so we're going to start with case 1, where at least one of them is odd. It works if one is odd, it works if both are odd. But either way, you need one of them to be odd. All right, so let me show you. We're going to work through one so you can see what the process is. And so an example of case number 1 would be something like this. The integral of, let's say, sine cubed x cosine squared x. All right, so that's what I'm talking about, where one of them is odd. All right, now the key to this one is U substitution. Just think about when we try to do U substitution. Like if I were to ask you to do some sort of a U sub here, you would probably pick U equaling sine or U equaling cosine. And here's what's really nice about that. The derivative of sine is cosine. The derivative of cosine is minus sine. They're related to each other. So here's what we're going to do. Remember how I said this works if one of them is odd? Pick the one that's odd. If they're both odd, you can pick whichever. But pick the one that's odd and do this. I'm going to rewrite this as sine squared x times sine of x times cosine squared x. I'm pulling one of them out. So here's what I'm going to do. That one that was odd. I'm going to save this. I want this to be the du. I want that one little piece to be in the du from my u sub. So if I'm going to do that, I want the sine of x to be my du. Then what would my u be for substitution? What function has a derivative of sine?
Cosine.
Cosine. All right, so if I want that to be the du, then my u is going to be cosine of x. So watch what happens if I do that. All right, so my u is cosine, my du is a minus sine x dx. So if I start replacing, I'm going to have a sine squared. I'll have to worry about that in a second. I've got a cosine squared, u squared, and then the sine x dx becomes a minus du. All right, so up to this point, yeah, you've seen this trick before. But now we need to replace the sine of x. And this is where we go when we go back to our, well, we know what u is equal. Can I do that? And this is where our identities come in handy. Just think about that Pythagorean, the first one that I put up there. Sine squared plus cosine squared equals 1. Sine squared is actually equal to 1 minus cosine squared. And I know what cosine is. Cosine is equal to u. And so I was able to take this trig integral and do a u substitution on it. And it turned into this. Let's go ahead and finish this out. This is the integral of u to the fourth minus u squared, if you distribute. We'll come back to that in a second. Integrating this gives me u to the fifth over 5 minus u cubed over 3. And if I turn that back in, so using the u substitution, this is cosine to the fifth over 5 minus cosine cubed over 3 plus 6. So we were actually able to take care of this using a u substitution. the replacement of all the other stuff required using the Pythagorean identity. So the reason that this works, where one of the exponents is odd, is that we get to save one of them for the du, and we make all the rest of them, we turn all the rest of them into the other trig function using the Pythagorean. Okay, so let me kind of put down in words the process, what we do here, right? And then we'll do another example. So basically, here's what you do. If one of them is odd, so case one exponent is odd. What you're going to do is you're going to let u equal the other one. Right? Because we've got sines and cosines. So you're going to let u be the other one of them. Then you're going to do u substitution. And then you're going to replace any of the remaining using the Pythagorean identity. Because anything else that remains, you're going to be able to use the Pythagorean identity. So as long as one of the exponents is odd, you can do this. So let me show you another example. And this time, I'm going to make it so that both of them are odd exponents. And you're going to see that it still totally works out. So let's say we've got sine cubed times cosine to the fifth. So for this one, since they're both odd, it doesn't really matter which we pick. So I'm going to let u be sine of x, just because I need to have something, and I'll show you how this plays out. So let's let u equal sine of x, because it's the one, if we think that cosine is the one that's odd, then sine's the other one. So u is cosine, then, or sine, sorry, then du is cosine of x dx. So if I start replacing, we're going to have an integral of u cubed times cosine to the fourth x times du. Because one of those cosines got lumped into the du, right? So it went from 5 down to 4. But now I need to replace that cosine to the fourth, and I'm going to do that using the Pythagorean identity. So think of this as cosine squared squared, and cosine squared is 1 minus sine squared. But sine is equal to u. This is u cubed times 1 minus u squared squared du. Okay. Well, this is just a polynomial. If you were to multiply that all out, you FOIL this and distribute, you're going to get u cubed minus 2u to the 5th plus u to the 7th which then is super easy. U to the 4th over 4 minus 2u to the 6 over 6 plus u to the 8 over 8 plus c. And we'll put back our u. So we get that this integral is sine to the 4th over 4 minus sine to the 6th over 3 plus sine to the 8 over 8. So the other nice thing about this, just FYI, once you do all the u substitution, you're going to be left with just a polynomial every time. Those are easy. So we front load all the work. We do all the work with the identities and stuff. Once that's done, integration is a piece of cake. All right, so there's case number 1. That's what we do when we've got an odd power. And in the case where they're both odd, you can pick whichever you want to do. If we were to have started this one with u equal cosine, the du would have been negative sine of x, would have taken one of those, replace, it would have looked different because your answer would have been only in terms of cosines, but they're going to be equivalent to each other. And you could see that by using the identities if you were so inclined. I would not recommend. Okay, so there's case number 1. So then case number 2, what about when they're both even? Well, we'll do that one on Friday. We don't have enough time today. So here's the plan for Friday. So Friday, we were scheduled to have a quiz. We are not going to have a quiz. I haven't gotten this other one back to you. I don't need more work piling up on my desk. So I'm going to give you a week off from quizzes. All right, so no quiz on Friday. We're going to have regular old class on Friday. So we'll start in here at 8:30. We'll pick up where we left off. We'll look at what do we do if they're both even? And that's where we're going to use the power reduction identities. And then we'll look at some other forms that involve trig, like things that involve secant and tangent and so on. And we'll probably even start getting into what's called trig substitution, which is where we substitute in with the trig function. All right, anyway, so that's what's going to be happening on Friday. Just more trig integral. All right. So other than that, I don't think I have anything to share unless anybody else does. No? All right. Well then, I will wish you all a good couple of days, and I will see you on Friday.